Okay, so wow. Okay, so welcome to our afternoon session. So we will have 4 talks. The first one is Christian Narayan. Well, never a talk got better fit in a workshop. The talk is called Coded Compressed COCO, Sensing Based, Uncoordinated and Unsourced Multiple Access. And please.
All right, thank you very much. I take it as a sign that I was destined to present this talk at the workshop. The coco in the title of the talk and the coco in the title of the workshop is a sign that I think I was meant to present this talk here. So what is this talk about? This talk is really about a low complexity algorithm for solving very large dimensional compressed sensing problems. There is an immediate context for why we need such an algorithm, and the context comes from multiple access, which is what I'm going to talk about. But I think of this as a more general algorithm for solving several other compressed sensing problems as well, and maybe I will just mention it towards the end of the talk. So the immediate problem we are interested in is the design of multiple access for what is now called as the Internet of Things, which is a critical component of 5G wireless systems. So I want to take a quick look at what is different in IoT from what we currently know as wireless systems. So if you think about current wireless systems, these systems are designed for a small number of users to connect to a base station. And when the users connect to a base station, you have reasonably large amount of information that they want to transmit to the base station. Now, because of this, the overhead in coordinating the users is fairly small compared to the amount of data that you have to transmit. So more or less, most systems are designed in a coordinated way. As opposed to this, we're thinking about systems where you have a very large number of devices, each having a very small amount of information that wants to send this information to a base station. And here, the overhead in coordinating these users becomes sizable compared to the amount of information that they have to transmit. As a result, we have to operate in a more or less uncoordinated paradigm. And so this talk is really about taking a look at how we should design multiple access schemes given that we have to operate in an uncoordinated way. So if you try to plot the number of devices versus data rate, the talk is really dealing with this regime, where you have a very large number of devices and very small data rates that are of interest. So multiple access is a very old topic. It's a little bit daunting to give a talk in multiple access now, given the plethora of results that are available in multiple access. So I want to take a few minutes to talk about why this multiple access problem is a little bit different from what we know to do in multiple access. So I want to start with a very quick review of what we know in traditional Gaussian multiple access channel. So in classical Gaussian multiple access channel, you have a setup where you have k users, and each user has, let's say, a b-bit message. The users are allowed to use the channel n times. And we typically fix k, the number of users, and we let n and b go to infinity, and you get rate regions for the multiple access channel. And we know how to find the capacity of this. We know how to find the rate region. But there are many assumptions that are made in this formulation, which are usually swept under the rug. I want to take a few minutes to talk about this. So the first thing is this. The most important thing is that every user has an identity, typically like an IP address or some other form which identifies the user, and then the user has some amount of data to transmit. In traditional multiple access, we assume that there is some other protocol which reveals the identity of the users to the receiver, to the decoder. Now, using this identity, the receiver and the transmitters can agree on some resources to be shared. So, for example, the decoder can tell which time slots to transmit in, which frequency slots to transmit in, or which signature sequences to use. So you are basically coordinated between the transmitter and the receiver, and more or less this is how traditional multiple access is designed. And if you, from an information theoretic perspective, if you just naively look at the proof of achievability of the multiple access region, it says pick these code words completely at random, for example. But in practice, everybody has a code book whose parameters are somehow chosen based on the identity. It could be a spreading sequence, it could be something else, but some parameter in the code is chosen based on the identity. And we know the multiple access region. In terms of coding, we know that the corner points in the region are easy to achieve. And the equal rate point in the region is much harder to achieve in terms of coding. But there are many results which show that you can get fairly close to the equal rate point on the multiple access region also. So for example, there is this idea of interleaf division, multiple access. Spatially coupled codes are known to get close to the equal rate point for a small number of users. There is what is called a spatially coupled multiple access. And finally, polar codes are known to achieve the equal rate point also. Yeah.
There's one more way, that's just shifting the packets.
I think the spatially coupled one more or less is like this.
You don't have to, you can consider it to be spatially coupling, but it's successive cancel.
Yeah, I completely agree with that.
Far the nicest.
Right. So in all these cases, however, there is something that's hidden in all these cases. If you're going to do the shift, for example, you need to tell which user to shift by how much. So in all these cases, it looks like there is something that you need to do which depends on the identity of the user. So what we want to do is to try to remove this assumption that the identities are known and then revisit the problem. So what we want to say is, so we are interested in a regime where the packet size is very small compared to the identity. So you want to think of the packet and the identity together as your data. So, and now because of this, we want to use a policy which is identical at every user. So essentially what you have is this, you have k subtotal number of users in a network. We assume k subtotal is very large, out of which a subset k is active at any time. And k itself is fairly large. We're thinking about like hundreds of users, not 3 or 4 users. And each user has a small message, and each user can use the channel a certain number of times. These numbers are put so that you have some context and some canonical numbers. These actually come from, I think, the LoRaWAN standard. Okay, so these 3 things are the key things that I want to talk about. The first thing is each user operates in an uncoordinated way, so they have to pick the exact same encoding scheme. Now, if you think of adding the identity of the user to your payload, if you think about the multiple access problem, then what the receiver really cares about is the receiver cares only about the set of messages that are being transmitted, because the identity is considered to be part of your packet. So if you think about what the receiver is trying to do, the receiver is trying to produce a list of k possible messages. So the k users have transmitted a message W1 through WK. You want to produce a list. You don't really care about who transmitted what, because it is fully symmetric. And our interest is really in the short block length regime, so asymptotic results in information theory are not the best benchmarks to use. And this problem was pretty much defined in this way by Yuri Polyansky. And in particular, he also looked at the probability of error as being the per user probability of error, instead of saying I want to get the entire set of messages correctly. And what he did is he derived, actually I'll talk about that in a bit. There is one other specific instance of this problem where each user does not even have any each user does not have any data to transmit, and the user wants to only transmit the identity. So this problem is called as the neighbor discovery problem. So in a neighbor discovery problem, a node wants to know who else is in the neighborhood of that node. So that is a special case of this where you only have identity, right? And again, you don't really care about who is transmitting what. You only want to know the set of identities. At the physical layer, I'm pretty much going to assume a fairly general model. I'm going to assume a simple model, but the results extend to the case when you have fading, when you have asynchrony and things like that, but I'm not going to focus on all that. We're going to assume it's a synchronous Gaussian channel with no fading. Most of these can be extended to the more complicated channels. Okay, so URI basically derived an achievability limit assuming Gaussian coding and maximum likelihood decoding. He basically assumed if everybody were to pick a Gaussian codebook and then looked at an exhaustive decoder, and he basically came up with some result like this. And he also showed that many other traditional multiple access schemes are quite bad. If you just did Aloha or treat interference as noise, it's quite bad. And Orr and Polyansky actually came up with the first scheme which was substantially better than Aloha and treating interference as noise. And this was sort of the inspiration for our work. So this was a very nice result, but it was still a little bit far away from what can be achieved, and we wanted to close this gap. And this is basically what I'm going to talk about. I'm going to talk about another scheme which closes this gap significantly. So the key idea is this. The key idea is to think of this, so we're going to call this as an unsourced multiple access problem because you don't care about the identity of the user. There is no identity for the source. So we're going to think of this as a compress sensing problem. So what we are going to do is this. Each user has some information bits to transmit. We're going to think of this message as an index from 1 to 2 to the b. And depending on the index, each user picks you can think of it as a code word and transmits this. So you can think of a code book which has 2 to the b columns and n rows. Now, there are several people in the network. Each person does the same thing. So what you end up receiving is the sum of these columns, right, plus noise. And essentially now you are in the framework of a compress sensing. So if you think about it, there are k users in the network who you are trying to identify, and their message indices are in this very, very long vector. And if you can solve this problem, you have essentially solved the unsourced multiple access problem. The problem with this, however, is that if you naively try to think of this as a compress sensing problem, the complexity is just incredibly large, right? The dimension of this vector is of the order of 2 to the b, and b is like 100 bits. So unless you have sublinear time algorithms for solving the compress sensing problem, it is completely impractical to solve this. And so this is our key idea. So our idea is to do a divide and conquer approach. So what we do is this. We take the b bits of information that you want to transmit, and I'm going to add p parity bits to the information, and I'm going to add this in some kind of a structured way. So what I'm going to do is, I'm going to take these b plus p parity bits, and I'm going to break this down into many subblocks. And we're going to break this down into m subblocks, which I'm going to call as slots. And so what you do is this. In each of these subblocks, you try to transmit just the bits in that subblock. So if you think about just transmitting this part of the packet, now this is a compress sensing problem too, but just that the dimension of the compress sensing problem is substantially smaller, right? And then I take the second part and then I transmit that using a compress sensing problem. I keep doing that. I have m slots and we have transmitted a smaller chunk of my entire data over these m slots. But the problem now is this. When you do the recovery of these packets, you get a list of k packets for the first slot. You get another list of k packets for the second slot, and you're going to get a list of m packets for the m slots. And the question is, how do you know which packet here goes with which packet in this list? So you have to somehow tie the packets together from these different lists, and this is exactly what the parity bits are doing. So what we do is the way you put the parity bits is such that every parity bit here is a random parity check on all the bits that precede that particular parity bit. So then what you can do is something like this. You can build a tree decoder, right? So you take each one of the packets in the first list, and then you look at one of the packets in the second list and you see whether this parity check would be satisfied if these two were to go together. If it satisfies, you accept the combination, otherwise you reject it, and you can keep going down like this. And then in the end, if you had only one path that satisfies all the parity checks, you accept it, otherwise you say there is an error. And so now the rest of the talk is about analyzing this scheme and saying what it can get you. So let's think about what the parameters in the scheme are and what the performance actually depends on. So if you think of this as a tree decoder, essentially what's happening is this. At every stage, you have a certain number of paths that have survived. So I'm going to call that as capital L sub I. Actually, L sub I is the number of erroneous paths that have survived, because the correct path is always going to be in the tree. And what you do is you extend the path, and then you are going to do a parity check on each one of those surviving nodes, right? So the parity check is a check to see whether this is a valid path. Now, the probability with which that check succeeds depends on how many parity bits were there in that subblock. So I'm going to say lowercase l sub I is the number of parity bits that I have used in the ith subblock. If I increase I, clearly I get a better probability of error, but I have to trade redundancy for probability of error. And finally, we have complexity. So I'm going to define complexity, a proxy for complexity, as the number of nodes on which I have to do the parity checks. So for example, if I have to do a parity check at this node, I count that as 1. So I ask myself, how many times do I have to do the parity check before I can decide whether there was an erroneous path in the end or not? And the main question to answer is this. How do you determine the allocation of the parity bits? How should I allocate my parity bits within the entire block, given that I'm going to use a fixed number of parity bits? So the trade-off is this, right? If I put all the parity bits at the end, the tree keeps on growing until the end. This is terrible from a complexity point of view. But it's very good from a probability of error point of view, because I have very strong parity checks at the end to help me decide whether these paths were valid paths or not. To the contrary, if I equally distribute my parity bits, I prevent my tree from growing at every stage. The price to pay for that is that these parity checks are weak, and I may be accepting one of the paths, intermediate paths, and so this can cost me in terms of probability of error. So the idea is this. So there are some details beyond this. I'll try to give a high-level description of what actually happens. So what we do is this. This L sub I, which is the number of erroneous paths that survive at stage I, this is a random variable. The complexity is also a random variable, right? Both these depend on how I have allocated my parity bits to the different subblocks. So what we want to do is to get some expressions for the expected value of L sub I, which is the number of erroneous paths at every stage, and an expression for the expected value of the number of nodes at which I have to do my parity checks. And it's possible to do both these. The main thing is that if you condition on the number of erroneous paths that survive at stage I minus 1, Li is simply a binomial random variable with parameters Li minus 1 plus 1, which is the number of paths at stage I minus 1. Each one of these paths get extended by a factor of k times k. Out of these, one of them is the correct path, so I remove that. And each one of these paths could be in error with probability 1 over 2 raised to I, because I have L sub I parity checks in that particular block. So if you write the expected value of Li, it turns out you can get a recursion for the expected value of Li in terms of the expected value of Li minus 1. It's basically just writing out this probability distribution, writing the expected value, and realizing that this follows this recursion. Once you see the recursion, now you can get an expression for the expected value of Li. Now what about the complexity? Well, the complexity, of course, depends on these Li's, right? The number of paths that survive is the number of paths at which you have to do the parity checks. So if L sub I paths were erroneous at time I, then Li plus 1 paths survived at stage I. Each one of them get extended by a factor k, and then I have to sum that over all the stages, and then there is a first stage k. So once I have this, once I have an expression for the expected value of L sub I can plug this into here, I can get an expression for the expected value of the complexity. So the next thing is to find some expression for the probability of error. What do I mean by the probability of error? What's the probability that a path, which is not the correct path, ends up being, survives at the very last stage? And to do that, you kind of have to use the same thing again. You use the fact that Li conditioned on Li minus 1 is binomial, and then you try to get a recursion. I'm not sure how much this particular expression itself is useful, but you can basically get an expression for the probability of error. And then the overall probability of error is given by this. The probability that the compressed sensing makes a mistake at any stage raised to power m. So if the compressed sensing decoder makes a mistake, then you have clearly made a mistake. And this is the probability that the tree decoding process does not make a mistake. So 1 minus the probability of this gives you the probability of error. And then you set up an optimization problem, and then you say, okay, what do I want to do? I want to minimize the expected complexity over my choice of parity bits, how many bits to put in which block, subject to a constraint that I don't want to be in error more than some fixed parameter gamma. And I have a constraint on the total number of parity bits, and I know that my parity bits have to have integer values. You try to solve this problem, but this problem turns out to be hard. So you make some approximations. Instead of putting a constraint on the probability of error, you put a probability on the expected value of L sub m minus 1, and you relax the integer constraint, and then this turns out to be solvable. And you get some results which are fairly intuitive. So I want to parse the how the parity length gets allocated. So if you enforce a very stringent constraint on the probability of error, so if I had 200 users, I think in this case we had 100 bits of information, and we say that the total number of parity bits you can put is 90. I think you had 90 bits of information and 90 parity bits. This constraint is too stringent. You cannot get an allocation which will satisfy this constraint. But as you keep relaxing your constraint, you see that at first all the parity bits are towards the end. But of course the complexity here is huge. If you really want to enforce a very stringent constraint on the probability of error, this is what you have to do. But as you start relaxing your constraint on the probability of error, you see that the parity allocation moves more and more towards being uniform, because in this case the complexity becomes fairly small. So this is the trade-off that you have. And you can do simple things like, if I have this decoder, once I decode a path, I can remove this path from my received signal, and then I can try to do the decoding again, standard interference cancellation type analysis, and these are the results that we get when you do this. So this is the achievability limit that Polyansky derived, and I think this is Polyansky and Orr's earlier result. So this is the performance of the coded compressed sensing scheme. This is with just one iteration. If I do most successive interference cancellation twice or thrice, then I can get something like this. So this is about 4 dB away from the information theoretic limit for, I think, like 200 users, 250 users, and it even scales for more number of users. Okay, so I have only 2 more minutes. So what else can we say about this? So it turns out that we can do some asymptotic analysis. So we can say something like this. So far what I have showed is finite length. You give me a certain number of bits, you give me a certain number of parity bits, I'll tell you what the best way to allocate the parity bits is, right? Suppose you let the number of bits that you have to transmit scale with k and n. The number of users, the number of bits, and the length, everything scale. Then you can ask, how does this algorithm compare to a plain vanilla compressed sensing algorithm? So in plain vanilla compressed sensing, you have a certain number of samples that you require to solve the compressed sensing problem. You require a certain complexity to solve the problem. And you can ask yourself, how does this scheme compare to that? And it compares quite favorably. So what we did is we studied 2 scaling regimes. In one regime, the number of bits that you have to transmit is scaling logarithmically with k. So this is like saying, if I want to identify myself, I at least need log k bits to send. In the other regime, the number of bits I have to transmit is scaling linearly with k. I don't really have a good justification for this. This is at this point just a mathematical curiosity. What would happen if b were to scale with k at this rate? If you did a plain vanilla compressed sensing, then what you would need is this. You would need a sample complexity which is roughly order of k log k in this regime. And in this regime, you would require order of k squared. And the complexity will be poly k raised to alpha in this case, and poly 2 raised to k. So this is really, really bad. right, in this scaling. But if you apply our algorithm and you do the analysis, essentially this is what you get. So you are order optimal. This algorithm is order optimal, which means you require the same order of samples as the optimal compressed sensing problem, but the complexity is substantially better. It is sublinear in the dimension. Instead of k raised to alpha, you get k raised to alpha over C1, and C1 is a constant that you can pick, such that you trade off the probability of error for complexity. If C1 is large, then your probability of error is somewhat large, but in all cases, the probability of error goes to 0 as k increases. So you basically get a sublinear time algorithm for solving the large complex compressed sensing problem with almost the same sample complexity. I think that's basically the message of the talk. I think we'll stop here. Yeah. Okay, thank you. I didn't really get a chance to talk about it. We basically assume a canned nonlinear least squares algorithm. So here is what we do. Oops. Oh, okay, maybe I didn't put it here. So it's a little complicated. So what we do is this. We solve a nonlinear least squares problem. Non-negative. Non-negative least squares problem, which gives you a list of possible messages. But this list can have more than k messages in the list, right? Then what we do is we threshold the values, create a smaller list, and then do a maximum likelihood decoder within this, which picks the best k values from here. Okay.
In particular, you need this condition that I think that the people who have developed the theory of NLS call M plus condition.
Okay.
Which is that basically there must be, I think, at least one row of the sensing matrix must have an intersection with the first octa. So, for example, you need like the all one row or something like this.
Okay. All one row in the matrix.
Yes.
But that seems like too easy to satisfy, right? I can always add a bit which is all ones to everything. That's
yeah, exactly. But this is
okay.
For the noiseless case, this is a necessary sufficient condition.
Okay. Okay. I didn't really know much of the literature on compressed sensing, so we didn't focus too much on that. But we basically use BCH code based matrices for compressed sensing.
We have been looking at your work, and I think that by chance you picked the right matrix.
Okay. Good to know. I call that intuition.
And the other issue is how you can make sure that the probability of error in the compressed sensing part becomes small enough.
Okay, so that's a good.
You have two types of errors, right? You have a misdetection and false alarm.
That's correct. So miss is bad. If the miss happens, it's bad. But false alarm is not bad, because I have this outer decoder which will stitch things together. So false alarm is not really bad. The miss is bad. So we haven't really analyzed that carefully either. But the simulation results are actual simulation results.
Can you find exactly what is the cost just by saying each user is multiplied by 0, 1? 0 means it does not operate, and 1 it operates, and this fading is constant for, say, for k channel users.
In this model, that is exactly the model. But I have simulation results assuming that the fading is drawn according to some distribution but kept constant for the n channel users.
No, the operation for me is fading. Whether you are active or not, this is for me the fading. Forget the
Yeah, that is correct.
And then the penalty, if you look at random coding, is not serious.
So the penalty is not serious in terms of data rate. The penalty is serious in terms of having to convey that information to the decoder. So for example, um, so the best results that we have actually, this is a result that I did not talk about. So what this is you just do IDMA. So it's like LDPC codes with sparse, like you take LDPC codes and then you sparsely spread it throughout the entire channel uses. But the problem is you have to tell the decoder which interleaver every user is using. Every user has to use a different interleaver. From the practical point of view, yeah. I mean, I'm not saying there is information theoretically there is anything here, but you need to be able to send that information to the receiver somehow. And I'm saying if you're going to send it, you should consider it as part of the coding scheme, because to send that you will need a compressed sensing scheme anyway, right? Yeah.
Has there ever been studies on feedback here? Because what I don't quite understand is that always gets ignored in these problems. It would seem natural to have feedback.
Yeah, so I think the model most of these papers consider, or we also consider, is that these devices are not acting with a very rich protocol on top of them. So the idea is that there is a very simple protocol at the MAC layer. So for example, what you assume is the base station sends the beacon periodically if you wants to get the information. If you are an active node, you listen to the beacon, and then you synchronize yourself based on the beacon, and then you want to send. I think that's basically the assumption. So there is not a lot of handshaking that's going on between the transmitter and the receiver.
Any more questions? Okay, so if not, let's thanks again the speaker. Okay, so our next speaker is Albert Guillen, and the title is Saddle Point Approximation of Error Probability in Channel Coding.
Okay. Can you hear me like this? Yeah, but I'd rather not. If you can hear me like this, then it's okay. Okay. So first of all, thanks, many kind thanks to the organizers of the workshop for inviting me over. It's a real pleasure speaking before you today. And I'll be speaking about something that, in a way, we've been working on for some time, and it's a way to compute some of the main bounds to the channel coding probability of error. Okay, and what I'll be speaking about today is mainly, I'll describe saddle point approximations to both upper and lower bounds. Okay, this is joint work with my colleagues in Josep and Alfonso in Barcelona and Gonzalo in Madrid. Okay, so I don't think that I need to spend a lot of time with this model. We'll be assuming the very basic channel coding model on a memoryless channel. Okay, and we will be allowing the output alphabet to be both discrete or continuous. Okay. So let me show you a plot just for the in order to motivate what we really want to do a bit better of the probability of error as a function of the EB over naught for one of our main coding channels, the binary input AWGN channel, for a high enough rate and a reasonably short block length. Okay. So I'll be showing here several bounds. The first one is Shannon 59 lower bound, okay, and which is still used today by a lot of channel coding people that work on the binary input Gaussian channel as a benchmark for comparing the performance of their codes, okay. And this is Gallagher's error exponent upper bound, okay. So the error probability of the best code is somewhere between these curves, okay. So this is the random coding union bound from Polyansky, Poor, and Verdu, which has behaved similarly to Gallagher's, but with a better, much better prefactor. And this is the improved sphere packing bound by Wichmann and Egal. Okay. So, and this one here is the curve that we obtained by the metaconverse, bound from Polyansky, Poor, and Verdu. So in this case, for this setting, the error probability of the best code is between these two curves. Okay, and most of this talk will be about how do we compute a reasonable estimate of these quantities here. Okay, which are by themselves not necessarily obvious to compute, especially in a channel like this. Okay. So, as we know, the probability of error of the best code is upper bounded by the RCU and lower bounded by the metaconverse. And we'll start by the metaconverse. The metaconverse can be written like this, where this alpha 1 over m is the alpha beta function of the optimal Nyman-Pearson trade-off. Okay, and it can be written by the like this, with no optimization before, because we are assuming a symmetric channel. Okay, if we assume a symmetric channel, we can write the metaconverse like this. Okay, for any auxiliary distribution Q. Okay, so this is basically the error probability of a non-Bayesian binary hypothesis test that is testing between this conditional distribution for any x and an arbitrary auxiliary distribution Q that you pick. Okay, and it remains and the metaconverse remains a valid bound for any Q that you want. Okay, so the metaconverse, as we will see, will be able to write it as a maximization of the sum of two tail probabilities. Okay, thanks to a rewrite of the alpha beta function of the optimal Nyman-Pearson trade-off as a tail probability over distribution P. Okay, and then multiplying by eta, and here we have another tail, in this case the positive, the right-hand tail of the likelihood ratio on distribution Q. Okay, and here we subtract beta. Based on this, it's very straightforward to rewrite the metaconverse as this optimization here, where we need to evaluate two tail probabilities, this tail here and this tail here, of this log likelihood ratio variable. Okay. The RCU instead, we write it, typically it's written like this. Okay, so expectation over the minimum of 1, and then the union bound goes in here, so m minus 1 times this quantity here, that is the pairwise error probability. So this is the probability, assuming that we generate code words pairwise independently. This is the probability of generating a code word x bar, whose channel likelihood is higher than that of the code word we transmitted. Okay, so this is the very basic definition of a pairwise error event in maximum likelihood decoding. And this is how we traditionally write this RCU bound. Okay, so what we'll see now, I mean, it's a fairly straightforward, in this case, it's fairly straightforward rewrite, is that the RCU can be written as the tail of a tail. Okay, instead of the sum of two tails, then it can be written as the sum of, as the tail of the tail using this identity here. Okay, and this says that the expected value of the minimum of 1 and random variable, positive random variable x can be written like this, like the tail probability that x is greater or equal than u, where u is a 0, 1 uniform random variable. Okay? Independent of x, of course. And using this, we simply rewrite the RCU in this way. Okay, so we have we have this inner tail here, and we have this outer tail here, okay? So on the one hand, we have the sum, or the optimization of the sum of two tails, and in the other case, we have the nested tail problem, okay, the tail of the tail. So what remains is to understand how to compute this, okay? So for simple cases, already Yuri Polyansky computed these quantities here for exactly for the binary symmetric channel and the binary eraser channel. For some simple cases, this is easy enough. Oops, easy enough to compute. Okay, but in many cases of interest, it isn't, and this is the whole point of this work. Okay, so we can resort again to simulations to compute these quantities here. Again, computing tails or simulating tails is not a terribly difficult exercise, but if we want to go low on the probability of error, then it may become quite intensive. Okay. So what we'll be doing is we'll look into some refined asymptotics based on the saddle point approximation. Okay. And the saddle point approximation is an approximation that is well suited to study precisely tails. Okay, tails of sums of random variables. Okay, and this is one of the things that we're interested in. So, on a pictorially, let's try to approximate a PDF around this point here. This being the true distribution. If we used a Gaussian approximation, a naive Gaussian approximation with the same mean and variance, then we would get a fairly bad match in terms of approximation. We can use a saddle point approximation of this tail, which, as we will see, is also a sort of Gaussian approximation, but using the information that we wish to evaluate this distribution at a certain, the distribution of this tail at a certain point. Okay, and this approximation, in a way, converges to the real Gaussian as the point we evaluate the tail at gets closer to the mean, but it gets actually a much better approximation of the tail away from the mean. Okay, and this is precisely the point that we wish to study in the quantities of interest. Okay, so let me review some of the basics of the saddle point approximation. And then I will be showing you some examples, how to apply this to approximate both bounds, and some other examples later on. Okay, so we have n random variables, and that are, and we wish to evaluate the tail at point gamma of the sum of them. Okay. So if we write the distribution as with the inverse Laplace transform, taking into account that this function kappa of s here is the cumulant generating function, then we can rewrite the distribution like this. Okay. And now, in order to approximate the density, the first thing we do is we approximate this around we do a Taylor series expansion around some point s hat, okay, which gives us this here, okay, this term here. And now, if we perform a change of variables and we take s hat out and we integrate over the complex line, then there's this term that comes out here, from here, and then this part here. This part here. The s hat part of this comes out, and then the rest remains. Okay, and what is it that remains? This is the characteristic function of a Gaussian random variable. Okay, so the saddle point approximation of a PDF is given by this quantity here. Okay. So how, what do we do to get to the, or to approximate this tail probability here? So we plug this in, okay.
How do you choose S hat?
That was it. This is perfect timing. So S hat is, due to the convexity of a cumulant, is the unique point that you find by equating the first derivative to the point you wish to evaluate the tail at. Okay. So after some massaging of the expressions, and actually, so after some massaging of the expression, we obtain this approximation here. Okay. So where this is, again, this is the exponential term. Okay. One of the good things, something I forgot to say, is that one of the advantages that we get in this method is that it preserves the exponent that the quantities we wish to compute have, so the Chernoff or Markov inequality exponent that we would get, but in addition they give us a good prefactor. Okay, and these we can think of as some sort of modified Q function. Okay, this is fairly simple to compute. Okay, so there's nothing here. Actually, the way we find this is we plug here the original Laplace expression, inverse Laplace of the PDF. We exchange integration limits, and then we integrate first over z, and then over the saddle point. Okay. Anyhow, this gives us an approximation of this tail probability, and I've been using these approximate signs all along. Okay. Here we have terms that are of order 1 over square root of n. Okay. So the error terms are 1 over square root of n. So again, looking at the metaconverse, these are the two tails that we wish to approximate, and we get something like this. I mean, this is simply plugging in the expression that I showed you earlier. So we need to calculate these two cumulant generating functions for the two distributions of this likelihood ratio, and it so happens that they are related. Okay, thanks to the structure of this hypothesis test, of the binary hypothesis test, these cumulants are related. So the kappa 0 of S plus 1 is equal to kappa 1 of S. Okay, which in turn, for our case, for memoryless channels, it means that, or IAD distributions, it means that it factors as n times one single kappa of S, okay, which can be easily written and computed in this form. Okay, so this is a single dimensional integral. Okay, so here there's absolutely no difficulty in computing this. Okay,
Can I ask you a question?
but of course.
So that is an integral is written y, but
Yes.
it contains x.
I'm sorry.
But it contains x.
It depends on x, but again, you can pick any x because of the symmetry. So we are assuming a symmetric channel.
Yeah.
Okay.
Okay. So here x is discrete.
Yes.
So if you
Yes.
for plus and minus.
Plus or
then
yes.
it doesn't matter.
Yes. Exactly. So again, computing kappa prime, the first derivative, or kappa second, these are all single dimensional integrals. So this is a fairly easy computational exercise. Okay. And now let me briefly touch on the output distribution, okay, that we can choose freely. So one distribution that we choose is this one here, is the one that meets, one output distribution that we choose is the one that meets the sphere packing exponent, okay, for obvious for fairly obvious reasons. Okay, and this is related simply to Gallagher's Z0 function. So basically, the cumulant is just a direct function of Gallagher's Z0 function. Okay. So what have we done so far? Recapping this part, we have shown that the hypothesis testing setup as a maximization over this parameter can be turned into a maximization over some parameter S, and we have a saddle point approximation, and we set this exponent achieving distribution Q. Okay, and combining these, we get this expression, which is the one that we use to compute. Okay, and all quantities here are very simple to compute. Okay. Okay, so let me move on to and again here we can guarantee that the error terms decay as 1 over square root of n. Okay, so in this case. In this case, we can give guarantees on the error that we incur.
But there's no, you can't get a firm bound, right? It's an asymptotic.
We cannot get a firm bound. It is an asymptotic expansion indeed, thanks to the very first Taylor series expansion that you do.
It's an approximate bound.
It is indeed an approximation. It is indeed an approximation, yes. Okay, so we'll try and do more or less the same for the RCU. So this is the RCU in tail of tail form. Okay, remember that now we have the tail of the tail. Okay, so this inner tail probability is in itself a random variable. Okay. So what do we do? For fixed x and y, we can do a saddle point approximation of the pairwise error probability. Okay. So what is the kappa of the pairwise error probability? It's simply given by this quantity here. Okay, this being the random variable that over which we calculate the tail probability. Okay, and this kappa minus s hat z, okay, ends up being by very simple manipulations, since z is this quantity here, is the logarithm of y given x, okay, we get to a fairly familiar expression, okay? So kappa minus s hat z is the minus generalized information density, okay? Which is indeed the exponent of this approximation. So the pairwise error probability is approximated by this, okay, where this is the exponent of the pairwise probability of error, the minus information density. And this is a term that, as you see, I mean, it's a bit convoluted, but it has nothing apart from first and second derivatives, okay? So in principle, S hat should be depending on x and y, okay? Because this saddle point approximation does depend on x and y, okay? But of course, this will compromise the computability of this bound. Okay, so we actually choose not to. And therefore, we carry these first derivatives over. Okay? So now we go to the outer, to the approximation of the outer tail. And we rewrite it, so we substitute our approximation to the pairwise error probability. And this is indeed the tail that we wish to evaluate. Okay? U, again, remember, being a 0, 1 uniform random variable independent of x and y. Okay? So if we set S hat equal to 1 on 1 plus rho, where rho will be the saddle point of the outer tail, so indeed S hat does depend on what you are computing in this outer tail, but not on the explicit x and y. Okay? And we can rewrite, well, we can, again, approximate this cumulant by looking at this structure here. We rewrite it like this, okay? Where this function phi is a tilted expectation of this variable here. Okay, and this is the tilting, precisely using the fact that the pairwise decays with this exponent. Okay, and finally we run the final complex integral over rho, and then we're done. Okay, so again, summarizing, we approximated the pairwise error probability. We set the saddle point, the inner saddle point, as 1 on 1 plus rho, and then we perform complex integration, again setting this thing here. Okay, and combining this, we get this approximation for the RCU. Okay, where again all the quantities are very simple to compute. However, here we have a difficulty. Okay, and this difficulty is real. Is one difficulty that we are facing right now. I wouldn't say we're making some progress yet, but we have a hope of making some progress. And is that thanks to the fact that we have a nested tail, controlling the error terms is difficult. So let alone bounding them, but even the approximation itself is very difficult. Why? Because we are not setting a saddle point that depends on x and y. The saddle point that one should be choosing is the one that sets the first derivative of the cumulant equal to the point we wish to evaluate the tail at. Okay? And here we decided not to do it for the pairwise error probability, for computability reasons, and therefore it's very hard to evaluate how this plays. Okay? What exact role this has. As we will see in some plots, the effect is not very big. Okay? So let me show you some curves now. Okay? First, for the binary symmetric channel. So we have the sphere packing or metaconverse lower bound here, and we have a Gallagher's. So I'm plotting error probability as a function of the length. Gallagher's bound here. Okay, so the first is the saddle point of the RCU. Okay, and this is the exact RCU. So the saddle point allows you to characterize even these wiggles in the curve. Okay. I didn't explain exactly the framework that we would use for doing this, because this in the BSC we have to deal with lattice random variables. Okay, but the principles are more or less the same. Okay. Then back to our binary input Gaussian channel. So let me show. So here we have again the same plot, error probability as a function of the length, and between Gallagher and Shannon's 59, we have here the RCU and the simulation of the RCU. Okay, so we see that the approximation is fairly good. Okay, it's again very hard to say how good it is, but actually to the eye, or to the engineering eye, or to the coding practitioner, the approximation is very good. Okay, and similarly for the metaconverse, and actually for the metaconverse, perhaps one would argue that it is better. Okay, I mean just recall or look at the order of these lengths. Okay, we're still speaking about very short codes. Okay, so n is fairly short, so the approximation is good enough for very short code, say length 20 or 30. Okay, so it's quite an interesting approximation in itself. So this metaconverse here is the one that we find if we use the Q that maximizes or that attains the sphere packing exponent. If we don't do this and compute the metaconverse for the capacity achieving exponent, we get this. Okay. So it's a remarkably or noticeably worse bound and definitely worse performance indicator. Okay. So this is a different plot, probability of error as a function of n. of these curves here. One perhaps interesting effect that one notices, but this is about the curves themselves, not necessarily about the approximation, is that, so this is the mutual information, and this is the critical rate, okay? And beyond the critical rate, or for rates lower than the critical rate, the exponent of these curves diverges, okay? This one here is known to decay with the sphere packing bound, and this one here decays with the random coding exponent, okay? So also, the only thing that one notices from these approximations is that they do characterize the exponent, the exponential decay as well, okay? So with this, I conclude. Thank you. Yep.
Just out of curiosity, especially in the previous plot, we have this very, very short block length. Like, for example, I don't know, 30. And the rate is a little bit more than 0.5. So this is basically 15 bits. So 15 bits is not a ridiculously enormous number of code words.
No.
So if anybody try to get points, I have actual code that goes in between these two bounds.
I'm not sure. I mean, still, you need to come with a construction. You cannot search in a 2 to the 15 space.
But maybe with the neural network you can.
No, I mean, you definitely can. But I know. Say,
So for these lengths, I mean, tail biting convolutional
I was about to say.
4,000 states with wraparound Viterbi decoding will, I'm guessing, include,
Yes.
I think it even does at least up to length
Yeah.
150 or maybe.
They're extremely close. Actually, Gianluigi Liva sent me some simulations that unfortunately I couldn't add, and they're spot on. Exactly, tail biting convolutional codes with lots of states, but they're still decodable with these lengths. Perform extraordinarily well. Yes.
PCH codes are quite good. Short polar codes with CRC and very long list sizes are extremely tracking. I would guess that it falls.
But for length 30 as well?
Maybe 30 is too low.
30 is low enough.
100, yeah, somewhere around.
Beyond 100, I think it starts being.
There are codes that are in between these two curves, basically. The blue and the red.
Yeah.
Like the very short lengths, even up to past length convolution, I'm quite sure.
Yeah.
But it's worth plotting once, just taking his performance.
Yes, I actually need to dig them out because I once plotted it and now I totally forgot. But if I find them, I'll definitely show you because they're interesting curves. Yeah.
Question? Okay, so let's thank again the two speakers.
Thank you.
So the next talk is Pei-Hong Yang, and the title is Polar Coding with non-binary 2x2 formats. I think you need to do it in that way.
This way?
Yeah, and you need to put this one in the
So, hello, my name is Pei-Hong Yuan. I'm working in Technical University of Munich for Professor Gerhard Kramer. And this is a joint work with my colleague Fabian Steiner. And it's also presented last week in Hong Kong for the Turbo Symposium. And first, also, it's about non-binary polar codes. First, it's introduction. So previous work from Arikan, he used the binary polar codes with the standard kernel, 1011. And in these two papers, they use Reed-Solomon kernels instead of the standard one to increase the distance spectrum. And these two works, they also call that non-binary polar codes, but the purpose is a little different. They want to use non-binary polar codes for non-binary input channel. And so in our work, we just extend very straightforwardly the kernel 1011 here to 10 alpha beta, and alpha and beta are elements on GFQ. And encoding is very similar to the basic to the binary case. Here NC denotes the code length in symbol. And with this construction, we introduce additional degrees of freedom during the code construction because we can choose alpha and beta, and how to choose it we will discuss later. And in our work, we only consider binary extension fields, GFQ, where Q is equal to the 2 to a power of a natural number. And the code length in symbol is NC. Code length in bits is NC times log2Q. And we use log2Q tuple or decimal representations for a GFQ symbol. For example, in GF8, d squared times plus 1 is equal to 101 or 5. And for a single symbol UI, first TI, so in our work, only first bits can be selected as frozen during the co-design. For example, GF8, the possible choice is 0 to 7. If the first bit is frozen, the choice is restricted to 0 to 3. If all of them are frozen, 0 is the only choice. And this is the system model. We just discussed BPSK modulation in this work. So the number of channel users is equal to the code length in bits. So the transmission rate is k divided by n. And we first add CRC and add frozen bits to symbol conversion, and non-binary polar transform, and channel symbol mapping. And here is a soft information converter, is to convert binary probabilities to non-binary. So here the PMF is a length Q PMF. And the dashed lines, the dashed box is optional because for some decoding algorithms we need a CRC check. The blue curve is for flip decoding, and the red part here and this times R is for list decoding. Then we just review message passing on non-binary graphs. So the message in non-binary graphs is not log likelihood ratio anymore. It becomes a PMF of a random variable A. It's length Q. And for multiplication and addition, to compute the probability of the PMF of A times alpha, we can find a permutation matrix pi times alpha, because the values doesn't change, only the permutation are changed. For example, GF4 with primitive polynomial 7, the pi plus 2, it's a permutation matrix, is equal to this, because we just changed the position of 2 and 0, like these two columns, and 1 and 3, these two columns, right? And of course, we have variable nodes update. It's like a repetition code. We have two independent observation of one random variable A, and the PMF is computed by this element-wise multiplication. And this symbol, B proportional to, means normalization is needed to ensure that the probabilities in PA is sum up to 1. And for check node degree, so we need a discrete and cyclic convolution as the same as in non-binary low-density parity check codes. It can be implemented via hard-mod transform. First, convert the PMFs to another domain, element-wise multiplication, and then inverse transform. And because hard-mod transform is self-inverse, so we just ignore the -1 here. So then we introduce how to decode polar codes with Q-array SC decoding. So the P1 and P2 are decoder soft information input, or the input from last level. And obviously, by using check nodes update rule for P1 prime, we have this equation. And based on the hard decision of U1 hat, we can compute here P2 prime by using this equation. And obviously we observe that here, which means the SC decoding performance only depends on the ratio between alpha and beta, not alpha and beta. So for the kernel selection, we just choose the optimal ratio between alpha and beta to maximize the single level polarization as follows. So we use a length 2 code, so we call it single level polarization. Set U1 to frozen, and also the decoder knows that. And U2 is uniformly selected or randomly. And encoded is a non-binary encoding, and modulated to n channel symbols. In this case, it's 2, because code length is 2 times log 2 q. And add noise and compute P2 prime. And the decoder doesn't know any information about U2, but so here, this value means the probability of U2 hat is equal to U2, right? And the design criterion is we find the alpha divided by beta, which minimize this one, equivalent to maximize this one. The probability of U2 hat is equal to U2. And the expectation here is evaluated via Monte Carlo simulation, and it's a simple example. GF8, primitive polynomial 11, and for different SNRs, we observe that the ratio alpha divided by beta, 3 and 6, always provide the strongest polarization effect. And it's interesting, it's always group-wise. For example, 3 and 6 are the best one, and 4 and 7 are the second best one. And then it's 2 and 5. And the reason, to be honest, I don't know. And so then we just extend also some existing decoding algorithms to Q-array and compare them. And so the simulation setting is we use a relatively high order GF, and primitive polynomial is 285 because it's default in MATLAB. And alpha is equal to 29, beta is to 21, so the ratio is 29. Lensing symbol is 128, 512 information bits, and the frozen bit selection is via Monte Carlo simulation for SC decoding at 2.5 dB. And following decoding algorithm, I've investigated SC decoding, BP decoding, SC flip decoding, of course SC list decoding. We begin with belief propagation. So we just followed the pipeline implementation from Erican's paper, and we add a earlier stopping criteria, which means after every single iteration, we check whether U times G is equal to C. If so, the decoding is stopped. So we can see these two curves because different maximum iteration number. And the gray curves are as a reference. They are non-binary regular LDPC codes with variable degree 2. So it's 0.5 dB better than non-binary polar codes. So it's fine because polar codes is not designed for BP decoding. And so this plot shows the complexity of this decoder. So average complexity of decoder. We use the average iteration number. So we can see in higher SNR region, the complexity is converged to 2 or 2.5 or some. So because at higher SNR region, maybe only 1 or 2 iterations is needed. So then SC flip decoding. So due to the serial nature of SC decoding, we have two types of round decision. The first one is caused by channel or caused by noise. The second one is caused by belief propagation because we have some wrong decision before, so I cannot make the correct decision. So this plot shows if block error occurred, so the distribution of number of errors crossed by channel. So for example here, at SNR 2.25 dB, 99%, we have 99%, we only have one errors crossed by channel, which means if we have a Oracle added SC decoder, which can always fix the first wrong decision, the error probability could be 100 times lower, because 99%. And so if we want to implement that, an outer code is needed, because we have to check whether output is a valid code word. So we add this quote, because in non-binary, maybe it's not flip. It becomes symbol. So we add a length 16-bit CRC and stored the soft information in a matrix lambda. So if mu is a possible selection of UI, we just store the ratio between the probability of mu and the highest. So the SC flip decoding will first run the SC decoding, normal SC decoding, and store this information, and then find the largest element in this matrix in case lambda IU is found. So it will restart SC decoding again by changing UI hat to mu, okay, until one valid output is found. So it's the performance. So we begin with this orange curve, which means Tmax is equal to 0, is equivalent to SC decoding. And this black curve is the SC01 decoder, it's a SC decoder which can always fix the first wrong decision. It's approximately 100 times lower, -3 to -5. And so we need a flip decoder to approach this performance. And here, for SCF decoding, the average complexity is estimated by T average, the average restart time of SC decoding, and +1, the first SC decoding. And that high S1R region is also converged to SC decoding. Average complexity converged to SC decoding. And of course, list decoding. The path metric is defined as the same as the list decoding paper and initialized by 1, and it's always normalized to avoid numerical problem in programming. And we also propose list decoding with a prunet tree. So the idea is just delete the unreliable decoding paths, although they are the error most likely. So we first sort the error largest path matrix, and we have SPM is sorted path matrix, and eliminate the decoding path indexed by error if it's delta 1 times unreliable than most likely, or it's delta 2 times unreliable than the next more reliable. So it's limited. And so just performance. From here, we can see, so in this case, SC error case, we use the average number of visited nodes in the decoding tree to describe the decoding complexity. For example, the SC decoding, it's NC, because only the nodes in the most likely passes visited. And the decoding complexity of SC error decoding is approximately error times larger than SC decoding. And by using our decoding with a pronate tree, that you can see the performance is almost unchanged, but the complexity is significantly reduced via increasing SNR and also converged to SC decoding. So the average complexity is converged to SC decoding. And also with CRC, it's almost the same result, right? So the performance loss is negligible, but the complexity is reduced. And as conclusion, so we just extended polar codes to non-binary, very straightforwardly, and selected the kernel by maximizing the single level polarization effect. And we extend the BPE decoding, SCF decoding, SCR decoding to non-binary, and propose the SCR decoding with a pronate tree. As future work, first of all, a Monte Carlo-based co-design algorithm is needed. Maybe it could be based on density evolution or this property of UPO. And of course, higher order modulation. And maybe kernel selection for distance spectrum, because by extend this Erican kernel, we have alpha beta is 2 more degree of freedom, but now we just use 1. We use the ratio, but beta is still free to choose. Maybe we can choose beta to get a better distance spectrum. So, thank you.
Question?
Where's the 5G LDPC?
No, it's not 5G LDPC code. It's 5G binary polar code.
Yes, and where would the 5G LDPC code? Do you know approximately how good it is here?
It's better than the polar codes, I guess. No.
Any more question? Okay, so if
So thank you.
Thanks again, the speaker. And our next speaker is Boaz Shuval on Technion, universal polarization for process with memory.
All right, so this talk is called Universal Polarization for Process with Memory, and it's a joint work with Ido Tal. And what I'm going to talk about is a setting where we have communication under uncertainty. And the exact model is where when the encoder knows that the channel belongs to some set of channels, whereas the decoder knows the exact channel statistics. Maybe it obtains them using channel estimation, for example. We're going to allow for memory both in the channel and in the input distribution. And we want to find a universal code. That is, it has to have vanishing error probability over the entire set of channels, and we also want it to have the best rate possible. That is, it should have the informal information rate over that set of channels. And of course, we want this code to be polarization-based. Why? Well, we all know that polar codes have very many good properties. They are rate optimal, even in settings with memory. They achieve vanishing error probability. They have low complexity algorithms for encoding, for decoding, for construction. However, all of these nice properties come at a price. Polar codes must be tailored to the channel at hand. But sometimes this is not the case. Maybe in a wireless setting, for example, we're not able to know the channel in advance. Say we have a channel with frequency selective fading, then we might encounter intersymbol interference, where the received symbol at time n would be some linear combination of the current input and past inputs plus some noise, and maybe these channel coefficients are not known in advance. A different case, maybe flat fading, where we encounter a finite state channel and we may not know the transition probabilities or the states. of course, the decoder may estimate these coefficients so that we may assume that the decoder knows what the channel is upon decoding. Let me just give you a really quick reminder about polar codes, just to set the stage. So we have a channel. The input sequence to the channel is X. The output sequence from the channel is Y. And our goal is to decode X from Y. In polar codes, we do the following. We introduce one-to-one and onto transform FR-econ. It's a recursively defined transform, and it transforms the sequence X into the sequence F. Now, because this is a one-to-one and onto transform, decoding X is the same as decoding F. So we're going to decode F and not X, and then we're going to find X from that. And how are we going to do that? Well, we're going to use successive cancellation decoding. We take Y1 through N, we're going to call that G1, and use that to decode F1. And we're going to assume that we decoded F1 correctly. Then we're going to take that decoded F1 and Y1 through N, we're going to call that G2. We're going to use G2 to decode F2. We're going to assume we decoded F2 correctly, and so on. So at time I, we compute GI from the decoded F1 through I minus 1 and the received output Y1 through N, and use that to decode Fi, and so on. The polarization phenomenon is that for any fixed beta less than 1/2, we split all of the indices to two sets. A low entropy set, this is a set of indices where the conditional entropy of Fi given Gi is less than 2 to the minus n to the power of beta. These are the indices where Fi is a deterministic function of Gi in a sense. And the high entropy set, these are indices where the conditional entropy is greater than 1 minus 2 to the minus n to the power of beta. These are the indices where Fi is basically a coin flip that's independent of Gi. And the polarization phenomenon is that for a large enough n, any index falls into either of these sets. The size of L plus the size of H is n. And this gives rise to the following coding scheme, which is a very, very simplified version of the coding scheme. If I is a low entropy index, we're going to use that to transmit data. Of course, we're not going to make a mistake when decoding it because it's a deterministic function of Gi, so we're not going to have a problem. And if I is a high entropy index, well, we're just going to reveal that to the decoder in advance. So yeah, it doesn't have any hope of decoding it, but it already knows it, so we're going to be fine. So this is a very, very quick reminder of what polar codes are. Problem, they're not universal. The sets L and H depend on the channel. And we need to do something about this. So we're not the first to have looked at universal polarization. There are previous works. All of them were for the memoryless case. Two works that came out at about the same time considered a setting that's similar to ours, only in a memoryless setting. Hassanin and Banke had two constructions, and Shashoglu and Wang, that's here, have another construction. And there are also a few other works on other memoryless settings. Our construction is based on the Shashoglu and Wang construction, and it's a simplified version of it that is also generalized. We allow for memory at both the channel and the input, and it consists of two stages, a slow stage and a fast stage. In the slow stage, we take a sequence X and apply to it a one-to-one and onto recursively defined transform F. It's not the same as FR-econ, it's a different F. I'll tell you about it later. And what we want F to do is we want something that we call eta LH monopolarization. Basically, for any given eta, I will show you that there's an n, and index sets L and H, such that either any index in the set L is a low entropy index, has conditional entropy less than eta, or any index in the set H is a high entropy index. It has a conditional entropy greater than 1 minus eta. And this stage is going to be universal. These L and H, I can tell you what they are in advance. I don't need to know what the process is. However, this is a slow stage. We're not going to have eta vanishing exponentially fast with n. So we need to add a fast stage. What do we do in the fast stage? Well, we're going to take m copies of the slow stage. And then we're going to take the first index from each of these low entropy sets and pass them through an Aricon transform of length m. This is going to be fast, going to have a very low probability of error, exponentially vanishing. We're going to take the second pair, the third pair, the fourth, and so on. So we're going to have L copies of Aricon transforms. So overall, we're going to have probability of error that's upper bounded by this. And the rate, well, we only used the indices in L. So the rate is going to be L over L plus H. For the remainder of the talk, I'm going to talk about the slow stage. The fast stage is known theory about Aricon transforms. For the remainder of the talk, I'm going to show you what the slow stage is and talk a little bit about the proof. However, first, I need to tell you what our model for memory is. So we're going to look at a process. The process consists of a state Si, an input Xi, and an output Yi. We assume that the number of states is finite, so Si belongs to some alphabet S that's finite, and the state is hidden. It's unknown both to the encoder and to the decoder. We assume a Markov property, the probability of the state at time I being Si, the input being Xi, and the output being Yi, given all of the states and the inputs and the outputs in the past, is the same as if I'd only given you the state at time I minus 1. And it's not difficult to convince yourselves that we can always assume that what we actually do is we choose the state at time I based on the state at time I minus 1, and then we output X and Y probabilistically based on the current state. It's the same, they're equivalent. We are going to assume something else about the state sequence, and we're going to assume that it's a fame state sequence. That is, the state sequence is a finite state, aperiodic, and a reducible Markov chain. That's why we call XY a fame-derived process, because it's derived from what we call a fame process. And the important property of fame-derived processes is the mixing property. If I take two blocks of the process XY, one from the very distant past up to time n, and the other from time m to the very distant future, if these are separated enough in time, if m and n are far enough apart, these two are going to be practically independent. And this is the mixing property. Unfortunately, the mixing property is not enough. We need something else for our proof. We need something we call forgetfulness. So we call a fame process forgetful if for any positive epsilon, there exists a natural number lambda, such that if k is greater than or equal to lambda, then the following two conditions are satisfied. The mutual information between the state at time 1 and the state at time k, given all of the inputs and the outputs in between, must be upper bounded by epsilon. And the same is true also if it's only given the outputs, not the inputs as well. You might think that this is redundant. Maybe one of these conditions implies the other. They do not. We have examples where one of the conditions is satisfied and the other is not. So both are required. And maybe a more surprising thing is that the fame property does not imply forgetfulness. And in a moment, I'll show an example of a fame process that is not forgetful. Having said that, we do have a sufficient condition for forgetfulness in our paper, and it also ensures that epsilon decreases exponentially with lambda. So I promise to tell you, to give you an example that fame does not imply forgetfulness, and this is the example. We have a process with 4 states, 1, 2, 3, and 4, and an output y. We're not going to care about x in this example. And y is a if the state is either state 1 or state 2, and y is b if the state is either state 3 or state 4. It's not hard to convince yourselves that this is a fame sequence. It's an aperiodic and irreducible Markov chain. Clearly, it's finite state. So if I don't tell you the output, as I run through the state, no matter where I started, I'm going to converge to a stationary distribution, and the state at time 1 and the state at time k very large would be independent. However, now let's see what happens when I give you the sequence y. So let's say I told you that I started at state 1, S1 equals 1, then that immediately implies that y1 is A. Now I tell you that y2 is maybe B. Well, there's only one possibility. S2 must be 3. If I then tell you that y3 is also B, there's also one possibility. S3 must be 4. So, knowing S1 and given y1 through k, I can tell you exactly what sk could be. So, there is no way that this mutual information would vanish when given y1 through k. So fame does not imply forgetfulness. However, there is an easy-to-check criterion to see if a fame-derived process is forgetful. So now, let me... does forgetful imply fame? Well, a forgetful process has to be fame to begin with. So yes. Now, so let me give you our main result in a simplified way, and I'll give you a more elaborate version later on. If a process xy is fame-derived and forgetful, the slow stage is monopolarizing with L and H that are universal. That is, they're not related to the process. So let me show you now what the slow stage is, and then I'll be able to give you a more elaborate version of this result. All right, so our slow stage is recursively defined, and I'm going to present it for the case where L and H are of the same magnitude. It's a transform that takes sequence X, transforms it to F. As I said, it's recursively defined, and it is initialized with two parameters, L0 and M0. At level 0, it has length that is twice L0 plus M0, and at every iteration, we double the size of their transform. At any level, we split the indices into two sets, the lateral indices, these are the top Ln and the bottom Ln indices, and medial indices. These are all of the remaining indices in the middle. And what I'll show you now is we have two operations. We have an operation we do on the lateral indices and an operation we do on the medial indices. The lateral operation is fairly simple. We simply take them and move them around. We take two blocks of level n. We take all of the lateral indices in the top of the two blocks and put them at the top of the new block, and all the lateral indices in the bottom of the two blocks and put them in the bottom of the new block. And we also sacrifice one medial index from each of these blocks and turn them into lateral indices. The medial recursion is a bit more interesting. First, I have two types of medial indices, an H-type and an L-type. And our operations are always going to take an H-type and an L-type and join them together in a way. As I said before, the first medial index of the first block and the last medial index of the second block become lateral, so we don't do anything with them. And then we take an H index from one block and an L index from the other block, join them, we get two new indices. One of them is an H index, the other is an L index. We take the next pair, H from one block, L from the other, join them, we get an H index and an L index. And so on, until we cover all of these medial indices that remain. Every time we take a pair, transform them, and we have a list of HL, HL, HL indices at the end. So now I could tell you a more elaborate version of our main result, and that is that if the process xi, yi is fame-derived and forgetful, then for any positive eta, there exist parameters L0 and M0 and transform size and threshold such that the slow stage of level at least and threshold is eta LH monopolarizing. And more precisely, if the entropy rate of the process is less than or equal to 1/2, then for all I in the set L, I can ensure that the conditional entropy would be upper bounded by eta, and if the entropy rate of the process is greater than or equal to 1/2, then I can assure you that for any index in the set H, the conditional entropy is greater than 1 minus eta. And I showed you what the sets L and H are. To conclude, I'll give you just a brief overview of our proof. And basically, the two parameters L0 and M0 are both related to the memory content of the process. We need to take L0 large if the forgetfulness is slow, and we need to take M0 large if the mixing is slow. And then the proof proceeds in two very big steps. The first step really replaces the slow stage with a modified slow stage and replaces the process with a different process that's independent in blocks. And we show that this different process and different slow stage are monopolarizing. In the second step, we show that if we choose L0 and M0 carefully, then this modification is actually the same, practically, as if we had used the original transform on the original process. And because that one monopolarized, then this one monopolarizes. And that's all I have to say. Thank you. Oh, I did not show you the condition. Basically, the condition requires two things. It requires the transition probability matrix of the process, but also the probabilistic method that you generate observations of the process. And I form submatrices in a way of the transition probability matrix, and if a certain product of them has a certain property, then we're fine. No, it's not trivial. It's not trivial at all. It's complicated to show. It's simple to check, but it's not a trivial condition in any way or form. Yes. No, we don't.
Okay, well then the second question was, or maybe it's just a suggestion, it could be really interesting for ISI channels where you usually use parallelization, you pay a price for the parallelization. You will probably polarize more slowly, of course, here, but just to figure out what that trade-off is, sort of in terms of the loss and length. So,
All right.
just as a thought, I mean.
That was going to be my question as well. So what do you pay for getting universality?
These codes are very long. Very long. Okay, that's something that needs to be solved. They're very long.
So the same probability of error, the length should increase by...
Yeah.
Sorry,
Yeah.
Can you estimate by how much?
So we do have we do have expressions for these, but I don't have your concrete answer at the moment. But we do have expressions.
The thing is, it's finite state, right? ISI is not finite state.
Well, why not? It is finite state.
The H's are continuous, so that's not part of
Well, if you fix H, then it's finite. Well, for any fixed H, it's finite state, right?
But if you don't
Okay. Yes. If I
capacity and you
yeah,
don't know the H's, it's
that's true.
not finite state.
can't you tailor, though, how much you're polarizing slow and fast, and then you could try to refine the results for certain classes?
Yeah. Oh,
like you
yes.
polarize
Yes.
faster and things. There's probably something you can still tune.
There's a lot of things we can tune. There's a lot of things we can tune.
Depend on,
Yeah, this is a very blunt instrument that requires very little knowledge. Knowledge would help greatly. No, I agree. This is a blunt instrument.
well, just because you may be trying to do too much, like trying to cover too many processes in practice, you may have a much
I agree.
set,
I agree.
and then you shouldn't be too pessimistic yet, because
Oh, I did not say I was pessimistic at all.
I didn't either.
Any more questions? Okay, so if not, let's thank all the four speakers. Thank you very much.
Quick announcements. First of all, tomorrow, lunch is